Hello? Yeah. Thank you. Okay, good evening already. So thanks for sticking around. So welcome to this last panel of today on AI enhanced next generation wireless communications. My name is Geert Leus. I'm from Delft University of Technology, and it's really an honor to moderate this panel here today, especially because we're celebrating Jorgo. So congratulations. Yeah, you probably remember. I think we first met. It was in ICAST 2000, so in Istanbul. So we actually had a talk in the same session. We're tackling the same type of problem, and then afterwards, yeah, we had a conversation, and you invited me to the group, and that was the start of a long-lasting collaboration. So I think half or a year later, I ended up in the group, and there's a picture of that. So that's like a year. Yeah, that's 2001 or 2002. The big question is, where am I, right? So there's a few criteria you can use. Okay, so and since then, you've been a great mentor and friend. So thanks for that. So let's continue with the panel. So let me start by introducing the panel members. So we have Professor Anna Scaglione from Cornell Tech, working on information theory, information networks, decision systems. We have Professor Ji Ding from UC Davis, working on also communications, broadband MIMO, cognitive radio. We have Michael Tsatsanis from Viasat, working on satellite networks, and then John Treichler from Raytheon, working on defense technology, communications, radar, that stuff. So we try to make it interactive. So if you have any questions or comments yourself, so just raise your hand, and then we will give you the floor. So the title is AI Enhanced Next Generation Wireless Communication. So maybe the first question we can handle is what do we mean by NextG, or what does NextG mean for you, right? With your expertise. So I don't know who wants to kick off. Let's see. See. Yes, I have. I will give you one. You can pass this one around. Oops. Yeah, maybe we don't need it.
Anyway. Is this the one that doesn't work?
Otherwise, you can use my. Yeah.
No, this will be fine.
You keep it straight. Yeah.
Oh,
so what does NextG mean for you guys? So with your expertise, so what do we have to think about? Is it like the reflecting surfaces, higher frequencies, molecular communications? Because there's all kinds of different types of NextG, or people think differently about NextG systems.
Okay, well, let me start off with intellectual honesty. Part of the reason I came to this workshop was not to just honor our local sponsors, okay, but to figure out what the devil 6G was and what people really thought it was. Quite seriously, and driven by two things, and I'll be brief, obviously. One is that in all of these progressions of technology you see, it's sort of the king is dead, long live the king. We get 1G done, and we pat ourselves on the back, and then we start a list of all the things that are wrong with it. And then we define 2G to solve all those problems, and then we do them, and then we pat ourselves on the back. Okay, so I'm not perfectly clear yet that we have actually gone through that assessment yet with 5G to figure out to what degree it doesn't satisfy our objectives, and even more important, there's actually somebody who has to buy 5G or 6G, pardon me, and it isn't you. It's actually the system operators. And I believe the system operators are absolutely unconvinced right now that 6G, whatever it is something that they want to spend another several $1 billion on to buy equipment. So I'm not meaning to say I'm intellectually uninterested in 6G. I'm very interested in it because we need to be thinking about what it means. But I'm saying that as a business and what it does and what features it's going to offer, what problems 5G has and so forth, I will admit to being a little bit of a Luddite. I can never imagine what people are going to do with all these bits. Okay, I figured as soon as we got up to stereo, 4K, video, and 18-channel of surround sound that we had all the bits that any human needed. And what I found out is there's so many cat videos in the universe, okay, that it overwhelms my desire to, my understanding of how many bits. So anyway, I'm actually very interested because we need to start making that list of what actually we need to solve, and the technical things you talked about, moving to higher frequencies and so forth, are possible solutions to possible problems. But I'm still trying to figure out, as an engineer and possibly commercially interested, what we're trying to go solve. And then once we figure that out, then I do want another shot at the question of AI and things. Yeah. But let's just talk about 6G first.
Yeah.
Okay.
Or NextG, right? Or whatever in your, yeah.
Yeah. So, all right. Well, I'm going to talk from my little corner of satellite communications that I know best. And I'll just summarize it in one sentence. I think NextG is a network that will introduce a tremendous increase in the complexity of the network, of satellite network. So complexity is the name. Now, let me qualify that. I mean, when you ask this question, there's two ways to think about it. What's NextG? One way is to kind of have the frame of mind of the researcher, you know, of the world, come from the world of ideas. You can say, well, maybe we can have quantum communications, or maybe we can have some esoteric materials or antennas or propagation modes of RF waves or whatever. So there's a lot of things that could come as new ideas. Some of them will pan out, some of them will not pan out. Maybe we can call that like the deep NextG. But I'm just speaking from the industry, and I'm just saying, you know, the networks that people are going to be deploying in the next 5 years, what are like the issues? What's the NextG problems? Rather than what potential technology may be used in solving some problems, some of these problems. So I come back to the complexity and satellite networks. So satellite networks traditionally have been thought of as simpler than the terrestrial networks, because a lot of times you deal with line of sight channels, so you don't have all these complications of fading. And because traditionally satellites were simpler networks. I mean, in the beginning of time, like in the 1980s, DirecTV and so on, people did broadcast television services. And this was just one satellite, one beam, or Biscay B in Europe or whatever, that would cover the whole continent, and you have 100 million receivers. It's one-way communication. You transmit very high rates, but there was some very interesting signal processing issues with challenges, the link budget, all that kind of stuff, phase noise. There's a lot of PHY issues. But as a communication system, it's not a complex communication system. Now, when the internet came along, this went out the window, so people moved to these high capacity or high throughput satellites and moved higher in frequencies in the Ka band. And it started with like 10 beams, 20 beams, 50 beams, 100 beams. My company was one of the pioneers in that the last 15 years. Now we launch satellites that have thousands of beams. So it's a lot of all the signal processing, beam forming, all that stuff, you know, just a lot of that stuff. But even that pales in comparison to what's coming, which is that you have mega constellations, each of which is tens of thousands of satellites, each of those satellites having hundreds of beams, and everything moves. So basically you have replication of the cellular network in the sky, where all the base stations are dancing around in the sky. So the issues of network optimization, resource management, allocation of resources, admission control, you just name it. Like, where do you put the users? What resources you use for each user? What are the service level agreements that you have? Like, how much is users gotta get? All these issues are mind-boggling. People don't know how to solve them. Now, those are a little higher up than the file layer. There's challenges in the file layer, don't get me wrong. There's a lot of challenges in the file layer, but I think if I want to summarize it, for me and from my little corner of the satellite world, NextG means how we're going to deal with all this complexity. That's the name of the game.
Thank you.
Okay, so I have to say I have not been working on wireless for a while, but I agree with Michael. The one thing that I think a lot of people talk about when I hear them talking about 6G is latency. And latency is not just a problem of the physical layer. You can send a lot of bits towards a base station, but that doesn't solve your problem of end-to-end latency. And even if we don't like Open RAN, the fact is the networks are highly programmable right now. Even the type of software that you use in edge devices changes based on code that is transferred opportunistically for the particular service. This is becoming extremely complex. However, I do have to say that we have all of this now understanding of how we do distributed optimization. We don't have to be stuck necessarily with the usual model where we divide and conquer. I remember working on cross-layer designs, again, a long time ago. And I remember Kumar saying, we cannot have this spaghetti structure. You have to kind of isolate problems across layers and spatially in the cell. But I don't know that these abstraction boundaries need to stay the same with all the capabilities that we have solving this sort of distributed optimization problem. And oftentimes, what you need is to coordinate locally. You don't need to coordinate globally because the problems are created by how you receive information in a certain swath of the network and in the corresponding swath on the other end where you need to deliver the data on time. So perhaps the 6G should deal with that. But it's not just going to be physical layer, although I understand that this community cares a lot about physical layer.
Well, thank you all for my panelists. Can you hear me okay? All right. Thank you for inviting me. All right. A lot's been said about 6G, but I'll go back to what John started off. I'm not exactly sure what is 6G. Right now, I'm not exactly sure what is 5G. The reason I ask that is, they are 5G coverages, but we're still using the same services. We're still doing the same things that we were in 4G. And so looking forward, the lessons we learned from the past should dictate what's in 6G. That's my personal humble opinion. Because it's the consumer products that should drive 6G, not RIS, not full duplex, massive MIMO. Those are only increasing the data pipes. Now, what people use for the data pipe is really at the center of 6G. So that's my opinion. So looking forward, I see that 6G should aim for services that are unique to be carried by the cellular network. So how many of us are using phones that doesn't have Wi-Fi? I don't think anyone here uses a phone without Wi-Fi. And automatically, when you get to an indoor or on campus EDU RAM, roam, when you have Wi-Fi, you go to Wi-Fi, right? Because that data is fast, it's free, and we're pretty happy with it. Now, so in my opinion, looking at it, what 6G should be is 6G has to be more than what you can get from Wi-Fi. And as such, because of a mobility, right, the Wi-Fi is less mobile, it's a little harder when you're out in the wild. So my view is that the 6G should aim for services that are unique, not just a bigger data pipe or faster. It has to be unique in, for example, outdoor scenario, in emergency, for applications such as smart health, agriculture. It's really the unique service that you can provide with the 6G that would win the day. And one prediction I'm willing to make is, we all remember that when 3G came about, and people will say, well, why do you need 3G? We're pretty happy when you have a cell phone, you can call people, because data, at that time, data was not the killer app. The killer app was voice. And for a long time, people say data is not the killer app. That's not that everything changed when the century came about, and especially when iPhone came out, and people suddenly realized, you can do a lot with a small phone, and that's when 4G has become such a big success. So for 6G to become a success, you have to win over Wi-Fi. You have to carry on your back the unique AI, that all the AI that are going to come, AI applications that are going to help us in smart agriculture, smart autonomous driving, all these above services that Wi-Fi is unable to support, or wireline is unable to support. Those are the scenarios and applications we should focus on. So I'm also going to say something that I feel that RRS is not there yet. All the reflective intelligence services, you look at the application, they are mostly for indoor, for something around the big building. It's not necessarily done ready yet for outdoor deployment. So I don't see how outdoor mobile scenarios will benefit a great deal from RIS. But for satellite, we can clearly see. So I totally agree with Mikhail about the complexity, because you need that to provide a omnipresent presence of wireless connectivity, and that you can carry the applications that integrate AI in your services. So in the future, in 6G, data plan has to be free, and you have to, just like voice now is basically free. Right? So data plan will need to be free for 6G to win, and you have to win, the carriers need to win on what services, what AI, what features it provides. The services is no longer faster data. The services has to be customized and integrated with AI. That's all. Thank you.
Thanks, Jeff. So, yeah, some interesting ideas. So, are there any comments or questions from the audience? Yes, Brian.
Yeah, so I agree with you. I think that, put me on mic. Thank you. I think that, now that we've got this wonderfully built out infrastructure and we've sprouted antennas all over the world and wired them all together, the questions now are things like dynamics, mobility, fencing, disaster response, right? Dealing with autonomy, and it's not just driverless cars, right? So you'd like to use AI for sensing in some area. You've got some weather situation, whatever it is. So I think that this question, I think for this community is, how do you couple into autonomy control, sensing, sensor networks, activating sensors, activating autonomy, all of these things that are going to take advantage of that infrastructure, right? That, as opposed to trying to make, more users per cell. I sort of feel like we're getting diminishing returns on our investments.
That's true. On the other hand, it's hard because you have to get in their domain. Because if you talk to people that do, for instance, smart transportation, right? They think everything is hunky-dory and everything works. They don't model the channel. So this is why I was mentioned latency in this type of control application may be really important if you're trying to platoon over a really large area network with 5G that has really tiny cells. But if you don't enter into the domain, it's very hard. And I can tell you from my experience in energy systems, right? I had to learn the domain because these people said, how fast can you transmit? I said, well, it depends, all right? Over an entire network. But I think there are still some principles that we are not exploring because we are so siloed in looking at physical layer. I hear right now that even 5G creates instability in TCP/IP, because now you have a front end which is so fast that the congestion control, and it's so fast changing, the congestion control doesn't work anymore. So there are things that we still need to do, and it could be also that there has been so much concentration in the companies that deal with these problems, that legacy systems is really hard to move forward. So that's my take on this aspect.
Actually, I want to go back to what Michael said. So as far as, I think one of the big differences between the cellular networks and the satellite networks are how the satellite networks are more proprietary, not based on standards per se, and have not seen the need to be based on standards, while the terrestrial network, the problems that you brought up are kind of standards based. So do you see that changing in the satellite world? Do you see the need for going towards some type of a standardized system? Otherwise, each one of you will be solving the same problem.
Yeah. The standards is a very tricky question, because standards have to do with lowering your costs on the one hand, and then speed of execution on the other hand. So if you're in a very fast-moving technology where, it's a land grab and you want to get there first, like, Starlink, they're not doing any standards because they just want to get there first, and they don't want anybody to slow them down. And that's also similar issues, vertical integration versus non-vertical integration. You can move faster if you just do everything your own and you just do whatever you want. But there's a penalty for that, which is that problems become harder and harder, and you need the brain power of the industry to solve the problems. So moving forward, clearly there is a tendency to standards, for sure. Another aspect of this NextG, I think there's a few dimensions. I just talked about complexity. I think it's like 80% of it. But the other dimension is that there's a convergence of terrestrial networks and satellite networks, and people want to use all kinds of assets that they have. So some people call them multi-orbit solutions or hybrid networks or whatever, because on a vessel or on an aircraft, you can have multiple antennas. You can have, typically you have like satellite Ka-band, high-speed antennas. You may have L-band, safety or mission-critical communications. So all these systems, they have to work together. We see in 3GPP that we have a non-terrestrial networks track where basically some 5 years ago people asked the question, well, we have this waveform here, this OFDM waveform. Will it work if we push it over a satellite? And the answer is no, because the satellite has this huge Doppler or has this delay or whatever, or the counters time out or whatever. And then it's like, wait, can we fix those things? And they did a little thingies to fix them. And a lot of people that are building these new networks now, even Starlink, which I said is not standards-based, it's almost standards-based. And other people are moving to standards-based. And also, we have this direct-to-device new networks, which are very important. Apple and T-Mobile and so on, they're doing different things where you just try to beam directly from a Leus satellite to your smartphone, which is, as Professor Palraz mentioned earlier, is extremely challenging from a link budget standpoint and other issues. But it's a new market. People are very interested in that, and all this development is going to be standards-based. So some of these issues, I'm going back to the complexity I mentioned before. The complexity issues will have to be discussed in the standards and in the academic community. And I encourage people to actually look at optimization of these networks across different layers and resource management and so on. Just moving up from the physical area. I mean, I've done this myself. Actually, I'm a signal processing guy, but the last few years I've been working on things like that.
Gotta take a minute. I'd like to give you one more answer, and you probably know this as well as anyone, but this is a business answer. Who wants, this is evil, by the way, who wants standards? Okay, the answer is the people who want standards are the people who want to buy the stuff the cheapest. Who wants to buy the stuff the cheapest? Well, it's not the equipment provider, the system provider. So actually, the first person to market who can get enough of the market has zero interest in a standard. Okay, because other people will come in. Let me mention a company called Google and various protocols in the network that they just went and did themselves. To heck with TCP and IP. I'm going to develop QUIC and HTTP2. And to heck with all of you. You might slipstream behind me. So anyway, I want you to think a little bit about the whole standards process. Because if, in fact, the marketplace continues to consolidate and it gets down to just one or two, I doubt very much they'll standardize. So think about that.
Okay, thank you. So maybe we move now to the AI part of the panel, which is the core, which is supposed to be the core, and we already touched upon it a bit. But yeah, the question is, what part of wireless can AI help? What areas within wireless would AI be useful, and what are the challenges there?
Well, I'm going to cheat and go first again, if you guys don't mind, because I've restrained myself before. Again, in the category of delivering bad news, this is not a PHY answer. Okay, and signal processors, we tend to live up at layer 1 and layer 0 and propagation. And it's also not a satellite answer because profusion of thousands and thousands of satellites is an incredibly difficult problem. But by some count, the part from the base station out to you is 1/8 of the system. The 7/8 down below, which is the iceberg model of wireless networks. Okay, as that moves to enhanced packet core, and there's just an incredible number of things going on and trying to build digital pipes essentially on demand between users as they move and so forth. And they say, oh, well, we're going to use software-defined networks, and the software-defined networks are going to be like really smart, and we're going to use AI. And I think they have no idea what they're talking about. But having just said that, the truth is that's going to be an incredible opportunity. Okay, when people figure out how to do that properly, I really think that AI, at least in the terrestrial networks, the most important application of AI to be effective is going to be actually in the terrestrial core, not in the air interface.
So also in the cross layer, I guess, then, not just one single layer. AI,
one can say, well, AI is great, we'll do AI and all that, but, we better say something more substantial here. So I'll just say from my point of view, the way I look at this is in terms of addressing kind of intractable problems or problems with extremely high dimensionality. I can see how if you impose difficult cost functions on the optimization problem, we usually kind of paper over that because we say, oh, well, we'll maximize the sum rate or whatever. I say, well, whatever, we'll just maximize something. But the truth of the matter is that stuff matters. If you're in a congested part of your network, you have different users, you have different service level agreements, different people pay different money, and different users use it for different applications. You can throttle who you're going to throttle, what you're going to do. All these things, like if you formulate what's my cost function, then it becomes completely intractable in terms of what is the model, the analytical model, like how my resource allocation maps to my output. And to me, that is reminiscent of problems like in reinforcement learning, where people were having these huge state spaces and they couldn't analytically model the policies, parameterize the network policy that you need to optimize. And they said, well, we'll just get the network to figure it out. We don't know a closed form expression of what the policy looks like. I think if there is ways to use this universal approximation property of neural networks and deep learning and be able to address optimization problems which are not easily very well formulated. Well, I don't know how to do that, but I hope you guys know, so you can tell me. I think that would be a good thing. So basically, again, I'm going back to my complexity, and I think that AI may have a role to play in complexity.
Yeah, thank you.
Yeah, I actually thought that there were nice applications of AI that both Rob and Lee showed. And I can understand how it can work there because you start having more complicated posterior, and in communication you are also trying to make that posterior advantageous with pre-coding. So in that case, you also have a model which is well defined. You have HX plus thing, but now that H has some vagaries, you either quantize or you put these analog front end that you don't know very well how to optimize and so on and so forth. So, and I can see how that can transfer, or you can train with training live on that particular environment. In terms of the complexity of networks, I am a little bit skeptical because it's too dynamic. So how would you create a digital twin that covers every possible resource allocation problem you are going to find yourself solving in the backhaul? I just really don't understand how you could possibly do it. So in that sense, and I saw
Me neither, that's why
but I saw a talk where somebody was saying I created this wonderful, test bed that can duplicate anything. And I have cell phones interacting with that. And I can show you how I did the optimum splicing over this network in the backhaul. And there are these 3 users. And then I tried to transfer this to another testbed. But again, there were these 3 users that were trying to do exactly the same thing. So I don't know how a reinforcement learning algorithm can be trained over all possible scenario over a digital twin. And there is no such thing as training the backhaul, right? You have all these costs changing constantly. So I don't know, much about how you will deal with that. Channel will be interesting to tackle is the channel. I think we haven't looked at overspread channels enough. We always have some kind of coherence. H can be estimated somehow, but that becomes a difficult posterior, and then maybe some nonlinear mapping could help.
Yeah. So I think there are also that we're trying to use the generative models now to find the distributions of these kind of complicated overspread channels.
Yeah, I couldn't agree more. Just even today, you from this morning, we have heard Yoram's talk that involves AI or machine learning, and Bhaskar, Lee, and just now Robert. They all have showcases how AI can be very important in solving complex problems for wireless communication network, wireless network design. So I'm fully sold on the usefulness of AI. In fact, now in retrospect, right, if you look back in the past, so before AI become like the how should I put it? Basically the North Star, right? Everyone is, well, not everyone, but many of us were, most of the community were very much in the mode of worshipping optimization. Like every problem has to have optimization, constraint optimization, and so on and so forth. Without that, you can't publish. And right, or you have to have a convex one because you got a global optimization. But then out comes AI, and deep learning says, I don't care if it's a global solution. I mean, it's a good enough a solution. So now that I think a lot of people are going 180 degrees, right? So everybody's going to AI now. So certainly, I think our community, we have some discussions this morning, right? We are at the unique position that we can understand the problem better, and with AI providing a good solution, can we simplify that? Because some of the networks are using hundreds of millions of parameters, and for that kind of parameter to be implementable and feasible on a small cell phone is still perhaps years away. So for that reason, I see that AI plays a very important role, but because of the nature of our work and our training, that we are in a very good position to figure out how to simplify the existing deep learning networks, not having to use the most complicated, say, diffusion model, most complicated large language model. Can we simplify that for our application? And that would really drive both the AI community and also leverage our strengths to solve problems better and more efficiently in our society, in this particular field, for wireless communication. And I want to say one more thing is that AI for communication, I think, is well proven. And the other angle is communication for AI, right? Because we would not be able to compete with companies. Companies have all the power and so forth. They develop massive models. They do the video animation. They generate videos. I mean, those are just amazing. But they have hundreds, if not thousands, of H100 NVIDIA, and I don't think any one of us can afford that. So for this community, we can consider communication for AI, because AI right now relies on a centralized computer, a farm of, like I said, hundreds of, sometimes thousands of H100 or whatever the media pushes out, H200. But they still need data. They still need to come to communicate a solution or to gather the data very quickly. And for too long, our QoS in communication networking is about human. It's like, we look at the picture, it's great. QoS, that's our QoS. Voice sounds great. Data fast, that's QoS. But how much have we considered the QoS of AI? Are we assisting AI? And I think that's where we hold the advantage. And if this community wants to attract more students again and to be a winner in this game, to basically one up on the computer science people who are very good at marketing their AI and whatever terminology, this deep machine learning, or whatever they come up with, then we, I think, need to leverage our strengths. So we need to be at the center of AI revolution by place the network for AI front and center. No longer network for image, for sharing pictures, for sharing videos, but network for AI. That's what I thought.
Good point.
Thanks.
Thanks. Any questions?
Okay, so when we talk about AI enhanced NextG, what you really mean is the application of the technologies we usually associate with AI for enhancing NextG, because nobody knows what AI is. We can just talk about the technologies of AI, isn't that correct? And so, G, what I hear you saying is that perhaps communication theory in its broadest definitions should be one of the technologies within this field we call AI. Is that what you're saying?
Partly so. That's sort of what I think, yes.
So in other words, not just optimization, not just network science, but in some sense the foundations of communication theory should be one of the technologies we associate with AI?
I fully agree with. I think so, because it's not. AI is an abstract term, right? Because a lot of discussion earlier we have heard that this is exactly what we used to do, but they just call it AI, or they just call it deep learning. But information theory and communication, in fact, is part of the AI because it's an enabler. And without the data transportation, without the signal processing, or in fact without the pre-processing, I doubt that you can do effective AI. In fact, for example, deep learning or facial recognition, it basically is extremely inefficient without good pre-processing.
Sorry, I am a pumpkin. I have to go to the airport.
Sure.
So it was a pleasure seeing everybody, and I'm sure the panel will continue.
Yeah, we will.
Thank you.
Yeah, we will probably handle one short question, one last question. So thanks, Anna, for your contribution. Okay.
All right, just wanted to ask quick question here. So we saw examples like like I gave where you can solve an optimization using AI, right? It fits within the standard because the standard doesn't tell you how to solve it, right? It says, here's some code books, figure out how to do it. So do you all see any problems that where the AI will need to be somehow specified or standardized? Like, and what does that mean? Are we going to see like, okay, this in the standard, your device is going to have to support an AI engine with this many layers and this computation? Or is there something, can you give us some idea of like, what does it mean for AI to be in NextG, if there's anything that's going to be fundamentally baked in?
Yeah. Unfortunately, I don't follow the standards that closely anymore. I used to, the beginning of 5G, I was a lot more involved. But I know that people are thinking of addressing these radio resource management and optimization problems using an interference-aware resource manager. And that means that, as Professor Powell says, that you're going to have a digital twin of the network. So basically, your resource manager would have to have an interference engine or a mapping of the network, understands antenna patterns and things like that. That's easier in satellite communications, by the way, because the channels are a little more well-behaved, not as ugly as in the terrestrial world. But anyways, so there is a question of what kind of data that resource manager would need, or that digital twin would need to faithfully represent the state of the network. So then whatever learning you're doing on the digital twin is representative of the actual network. And I understand that there's a lot of acrimony right now because a lot of people have privacy concerns, and a lot of people are trying to sneak in data that may or may not be needed by, and nobody knows what exactly these AI things are going to be, because these are things that people are thinking about and they haven't designed them. And so there is a big question about data. What is the right data that the standards should mandate that you get from the handsets, and what stuff and what is needed and what is superfluous and what could be actually a violation of privacy and all that. So it's kind of like a broader issue. And as I said, unfortunately, I'm not an expert on that because I don't go to every meeting. I hear that secondhand from people that go in my company. But that's what I know.
So, yeah, do you have a reflection on so my last question was actually a bit about the data that you already mentioned now. So what type of data are we gonna use? Is there enough data? Can we use simulated data from a digital twin, for instance, or how can we proceed in that direction? So, and then maybe if G can answer that, and then John can close off, and then we wrap up.
Maybe I can just tag on in an answer to Robert's question. I think that's a very good question. But my understanding of studying the standards 3GPP for over a decade now is that they don't offer solutions. They offer these are the steps. So for that reason, I do not expect that certain AI requirements are going to be put in there, like I said. But I certainly can see that they use all the requirements are in the standard. Like you need to get it done in 0.1 milliseconds and so forth. So that basically dictates that you have to be able to fit your AI model in a small device or in a larger device, let's say G-Node-B. And the reason for, I think there's, I'll go back to John's point, right? Because if you standardize what type of network needs to be in AI, then you basically snuff out the competition. And as I explained earlier, my view is that in the future, your service is not your data. A company like Verizon or say AT&T, they need to provide like AI-assisted services that the user says, hey, I like my service, not just because my data service is so much faster, but hey, it does this for me, right? It recognizes where I am. It recognizes my grandma fell down and it called ambulance. It needs to be that kind of service, right? It's not like, it's just faster and bigger pipe. It's like, what kind of pipe are you carrying? Is it a pipe of sewer or pipe of oil? So that's what I think. But back to the data portion, a few days ago, in fact, Hawaii and a few of us were at the NSF Spectrum Week, and that was exactly the issue. Is that we felt like for network level optimization, even for a physical layer, right? We simply don't have access to real data. I mean, unless you go out and measure, but we are not in a position to measure, broad-based cellular data like from different parts of the city anyway. So most of the data you see that university researchers and groups are doing, they're just measuring Wi-Fi data, which is kind of easier to handle. And for that, I also think for that reason, Wi-Fi is going quite a bit fast, about very fast right now. But for cellular users, we are not getting any data. And also, we're not getting any data from the operators. So the Ericsson VP basically responded to our question by saying, well, we don't have the data either because the operators won't share with us. And for various reasons. One of the reasons is that if they share the data, and for some reason the researchers said, oh, your network really is terrible. Oh, your network at some point is bad. Then it gave opening to their competitors to attack them, right? So it's like a politician would never admit they're wrong. And the network operators don't want to say their networks are not very good. But so that's really the challenge, I think, from our perspective, right? Collectively, we can see the lack of data basically prevents AI to become effective to address like the digital twin question, point that Michael brought up, right? How are you going to have all these many digital twins? Do I know I need to only have 400 for Minneapolis, 200? How am I comfortable with that? Because you don't go out, you don't have the data to do a real test and to demonstrate your success. So I think that's a real big challenge, and I have no solution. I don't know what solution there can be.
Yeah, true. Yeah.
That's uplifting. If I may say, now I have to say three things, and I'll try to do them quickly. Number one is I believe to Professor Heath's question that there will be possibly some circumstances in the future where standardizing in more detail than just it's got to be done in 2 milliseconds will be necessary. But I think most of it's going to be completely the other way. People want to use their AI as a competitive advantage and make sure theirs is better than anybody else, and will viciously resist any attempt to reduce the innovation they can do there. Number two, on the digital twin, I think we have to decide whether we're doing digital twins or digital cousins. A digital twin is, I know exactly what my system does, and I know what the environment does, and I duplicate it and optimize against it, which I think is fiction. Okay, digital cousin, I know what my system does, and I make a guess at what the environment might be doing. Okay, maybe. Okay, so I think that's where that stands. The last thing I wanted to say is actually to close a comment between Louis and Moss and I this morning. I wanted to just give you a little perspective before we all go off to eat dinner and so forth. Yes, it was the second DSP workshop in 1986 in Chatham Bars, and yeah, I was there. Okay, it was a great day, and we saw a presentation. A fellow named Steve Levinson, who some of you may still remember, he was at Bell Labs at the time. He did a demo of what we would now call a voice response system that they were working on. And you called it up with a telephone, and a human being said, United Airlines or whatever, what would you like to do? Okay, and it would recognize your speech and then make the mix. No, we have no airplanes that do that. It'll cost you $1 million, whatever it is that the airline would tell you. But the interesting thing about it was, think in terms of technology, deep neural nets, no. Neural nets at all, no. Hidden Markov models, yes. So it's hidden Markov models. And the key thing is that he had to present the presentation sort of on an audio tape, because when you talk to it, it actually went off and took 15 minutes to do the analysis to come back and give you the answer. And then you would say something, and then another 15 minutes. And so the whole transaction, in fact, took 8 hours of computer time. Okay. And so, yes, we've gone somewhere from Markov models, and to this I saw Alex Acero, who all of you know, at the 2010, what century are we in? The 2010 ICIP, and said, hey, Alex, is there anything to this deep neural net thing? And he looked at me and said, yeah, like this is scary. So just look at where DSP and AI have come in whatever that is, 26 years, 36 years or something. It's actually rather amazing.
Thanks a lot. So, yeah.
That's okay.
No, go ahead. Yeah, go ahead.
Hey, I just, this is outside probably the scope of this community, but I think that the whole issue of data governance and really data strategy for its operator, for its company. Data comes at all kinds of different timescales. This network is generating data at the millisecond level. You can get like queue lengths and all kinds of stuff. It's a torrent of data. You have to, and data costs money. That is to store, or how long are you going to store it? For an hour, for 24 hours, for 30 days, and what you're going to do with it, and how does it move around? And also, there's a whole area of software architecture technologies on how you manage these lakes of data, this torrent of data, and it's a serious obstacle. It's a serious obstacle in the implementation of AI solutions. It's something we don't really worry about, or there's nothing we can do about it as a signal processing people, but it's the other side of that page. That's a very important thing.
The system level.
Yeah.
What do we do?
No, I just want to remind those of us who were there that when did Jeff Hinton actually talk about their great discovery, which was at ICAST in Vancouver?
Yeah.
I mean, some of you may have been there. 2012, wasn't it? Oh, 2013.
That was 13, yeah.
2013. It was amazing, and the excitement. And of course, we know what Jeff has done recently, so let's keep that in mind.
Okay, if there's no more urgent question or comment from the audience, then I think we can close this session. So let's thank the panel members. And then we'll see you all tomorrow or for dinner.
It's dinner time.
If anybody needs a ride, I can drive to Caspian, and I can take 3 people.
I can take 4.
Thanks.